So we are considering this exercise. So when you have a C0 semigroup, then the application that associates T and X, so which maps T and X to ST of X, is continuous. So we are going to prove that. Okay, so how do you do that? So we have a normed space, so it's very classical. We are just going to look at the difference between S T plus H. So H is a small number, and we'll split in two. So H now is a small positive number applied to Y. So Y belongs to my Banach space X. And I look at the difference with ST of X. So here, T is a positive number, and X belongs to X. And so we want to prove that as H and Y converges to 0x, this is converging to 0. This quantity here, we want that as HT. So, sorry, HY goes to 0 plus X. That's what we want. Okay. So we need to do a few computations for that. What would you do? What would we do there? So it's like you work on R. We are going to introduce here X. I will introduce this quantity here. And then I have to add it again. And then I want this to be equal. So I need to write this again. Okay. I just need nothing, but that's good for what is to be done, what remains to be done. So now what can I do? So it's a norm. So the norm of so you have subadditivity. So I will split in two. So let me add one of these, or maybe two, three. Okay, so so I have that ST plus HY minus ST of X is less than ST plus HY minus ST plus HX plus ST plus HX minus ST of X. All right, so next, this is good. So, okay, this is we know that this is a bounded operator. It's by definition of a semigroup, And we know from the previous session that this norm is bounded. So more explicitly, I can bound this quantity here by, so let's do that, st plus h times y minus x. So this is in R plus. All right. And this comes from the fact that my s at time t plus h is a bounded linear operator, and so this holds. And here, actually, I can take out the s of t and do that times s of h minus x. Sorry, let's be more efficient here. Plus, so let's do in two steps, st times sh of x minus x. All right, everybody agrees with that? All right, so next, I know that exists a constant m and a constant omega such that this holds. So this is the exponential in R, right? This comes from the previous theorem, plus the norm of st applied to s of hx. Sorry. Okay. All right, so this converges to 1 as h and y converges to 0x. This converges to 0. So this is bounded, and this converges to 0 by definition of a C0 semigroup. So finally, that's it. This converges to 0 as hy converges to 0 plus x. Yeah, so here a bracket was missing, so thank you to the students. Brackets were missing here. All right. Yeah, so for the negative case, you are just going to, for example, put this quantity in front. Okay. Here it's okay because minus h is positive, so this is well defined. And then, so the norm here, I can bound it by this quantity. I have that, and this goes smoothly. So this converges. That's so the next exercise is just a simple computation. We just want to check with the simplest possible semigroup that this equality holds. So it's with a equals a is a real number, non-zero, and then the semigroup S of t is just the exponential of at from R to R. And yeah, just do this computation. So a simple computation here shows that the results, it's true. That's great, because if not, we were in trouble, because we already proved that for a much more general setting, much more general semigroups. All right, now theorem 4. We have some properties when you have a C0 semigroup, and those are the following. So first, for all positive t, for all x in x, so this result is well known for a continuous function, for example, from R to R. So it holds also for our C0 semigroup. Next, so for all x in x and for all positive t, we have that this integral belongs to the domain of A, and when you apply A to this quantity, you get stx minus x. So there's 4 items here. So item 3, so not the difference with the point 2 here, x is in d of A, not in x. And in this case, st of x is in d of A. And in this case, st of x is of class C1, and you have this formula, well known for ordinary differential equations, that when you take the derivative with respect to t of the semigroup, it's a s of t times x, and we will see by computation that this is equal to st of ax. And finally, you have this this formula, which results from the point 3, in fact, and you just see, since it's C1, this holds. So we are going to prove this theorem. All right, so let's start with the point 1. So again, in order to prove this this convergence results, we are considering the norm of the difference between the two expressions. So here you have that, and you were taking with the difference with that. Okay. Next, first, what I'm going to do, so I don't touch the first term. And here, so this is a constant. This so I just write it like that. I can write it like that. 1 divided by h t plus h times s of t x. So it's s. No, ds, right? I can do that. This is a constant. So I can do that. As I told you, this integral is very similar to the integral. So I'm integrating on R. So the values are on the Banach space, but it doesn't matter. This is true. Okay. This is true because integral between t and t plus h of identity of x, sorry, so of, yeah, so I can put it's identity, but it's well, it's a constant. So it's a constant. Let's do it. Sorry. So st of x is a constant and time ds. So I can take out the st of x, and then this is so if I can write it like that, and then it's yes, and then it's I can write it like that. It will be equal to, this will be equal to st of x divided by h times integral between t and t plus h of ds. And so, and here it's the integral from r to r. This thing is equal to that, and this is equal to st of x. So yeah, to say it works like an integral from r to r, even though the result is in the Banach space. Okay, what's interesting now is that I can say that this is less than 1 divided by h times st, so integral between t and t plus h of s of s minus s of t times x ds, right? I can let, actually I will do better than that. I will do like that. I will write it like that. So it's s of s minus s of s of x minus s of t of x ds. And now, I know that s of t of x is continuous with respect to t, meaning that when s is close to t, this quantity is small. So by using that, we know that this converges to 0 when h converges to 0 plus. So if you have any doubt on that, so this is exactly like you have a function from r to r. That's the case. That's the case because this norm now is a continuous function, and that works. And if you want to remind, so if you want the details, you can write, you fix any epsilon, and so this quantity here can be made as small as you want. This can be made as small as all epsilon you want if h is close enough to 0, and then you get that this is less than epsilon times h, which is less than epsilon. So for all epsilon, if h is small enough, you have this quantity that is smaller than epsilon, and this is exactly the definition of converging to 0. So one is done. So next we are going to prove the point 2 here. All right, so let's go. So here first, we need to prove that this quantity belongs to G of A. So in order to prove that, I have to consider the definition. So I'm going to look at SH of integral between 0 of T of S x Ts minus integral between 0 and T of S x Ts. This is the definition. So if this has a limit, when H converges to 0 plus, then this belongs to G of A. All right, so what I'm going to do is that I'm going to put the S of H in the integral. I can do that. So I obtain integral between 0 of T of S plus H x ds minus nothing changes in the other one. Next, I would like to have the same expression here. So I'm just going to make a small change of variables, and my new variable will be that. So I will obtain integral between H and T plus H of S x ds. I made a change of variables here, but I keep it, I keep calling it S because this doesn't matter. And then this doesn't change again. Okay, but here a lot of things cancel. So you can check that here. So I can split that between integral between 0 and H plus integral between H and T. But the integral between H and T will cancel on the other side. So I will get integral between 0 and H of S of S x Ts. And here I will keep only integral between T and T plus H of S x Ts. The remaining parts cancel. And then that's it, because this is going to converge towards St of x, and this is going to converge to S0 of x, but S0 of x is the identity. So I got the result. The quantity before converges to St of x minus x. So the point 2 is done. Any questions? So we are now finishing the proof of the theorem 4, and we are going to prove the point 3 and point 4 here. Okay, so let's go for the proof. So we want to prove that if x belongs to g of a, then st of x belongs also to g of a. So again, let's look at this. So sh of st of x minus st of x. And so I want to prove that this is equal to when h converges to 0 to st of ax. So first I start with h positive, and then we will see h negative. And so I will look at the norm of this. All right. Okay, let me write that here. So again, so I'm looking at 1 divided by h of sh st of x so minus st of x, and here h minus, I'm looking at st of ax. So what I can do, I can put st in front of everything. And I obtain sh of x minus x divided by h minus ax. Well, this converges to 0 because what? Because by our assumption is that x belongs to g of a, and if x belongs to g of a, the definition of ax is exactly this limit. So that's it if h is positive. Okay. What about h negative? So I do the same. So what we proved that st of x belongs to g of a. And so what did we prove? So we proved that first st of x belongs to g of a, and also that when I take the derivative on the right side, so let's write it dt plus of st of x is equal of st of ax. And by definition, this is also equal to A of STX. Because by definition, A is just a limit. It's a derivative, in fact. You compute A thanks to a derivative. So this is by just the definition of A. And this, we just proved it. Okay, now it still remains to prove that ST of X is C1. So to do that, I just need to prove that the derivative also exists in the other side, and that my result is continuous, but this will be true because we already proved that. So now H negative. So we are looking at now S T plus H of X minus ST of X divided by H. So I want to prove that this quantity is equal to ST of AX. All right. So since H is negative, I will do that. So here I have X minus S minus H. I can write that because minus H is positive, divided by H minus all right, so that's not bad because I can introduce AX here. I can introduce here. So let's write it a little bit different. I will write it S minus H X minus X divided by minus H. And I will write that and that. And what's going on now as H is converging to 0 plus? Well, X belongs to GA minus H is positive. So this by definition is AX. So this is going to converge to 0. Also, this is going to converge to yeah, also because S is continuous, so and AX, so this converges also to 0. By definition of a C0 semigroup. And then this is bounded. This is bounded. Okay, this is bounded by m exponential omega t plus h, and so we're good. And And that's it. So we proved that. What did we prove now? We proved that dt of st applied to x, this is equal to st of ax. And again, by definition, this is a st of x. Okay, now this is continuous, right? With respect to t, this is continuous because s of t is continuous. So finally, you have that st of x belongs to C1. All right, and so the point 4, I let you do it. It's just it comes just from this equality. So next, the 4 is just inequality. So let's write it. So if you look at the integral between s and t of a s tau d tau, now here I recognize that. Okay, so this is the integral between 0 and t of d tau of s tau x, forgot the x, d tau, and this is s of t minus s of x minus s of x. And we are done with theorem 4. All right, so the section 4, we are going to deal a little bit more with the generator of a C0 semigroup. And so we are going to see some properties about it. So first, we need a definition. So an operator A is closed if its graph is closed in x times x. So the graph is like a function from R to R. You look at dA and you look at the image of these elements, and you look at this this set in the product x times x. All right. So once you have that, you have this theorem. So in fact, when A is the generator of a C0 semigroup, then first D of A is dense in X, and A is a closed operator. Okay, so the proof is on the notes. I will let you read it by yourself, and it's not difficult with what we have done now. You should be able to read the proof, and so if you have any questions on it, just come back to me. All right. This is the proof, by the way, but okay, I'm just skipping that. Okay, also, yeah, it's not well written here. So assume that you have an operator that generates two C0 semigroups, S and T. Then in fact, S equals T. Again, the proof is interesting here. You can have a look at it, and again, if you have some questions, just come back to me next time. Okay, that's basically it for the chapter. There's also one exercise that's interesting to do. So you can try to solve it and look for the proof. I don't know. You can look for the proof in some books if you want. So if you have a C0 semigroup, then you have the intersection of d of an for all n, for all natural number n is dense in X. And so the exercise to solve this exercise, you can do it by splitting it in two questions. Sorry, so I'm going to do something like that so you can see the exercise. Yeah. Yeah, so I suggest also you can try to solve this exercise, think about this exercise. Okay. And so we will stop here for the chapter 1. And so the next chapter will deal with the Heil-Yoshida theorem. So that's it for today.